Hello and welcome back. Let's take a look at example 2. Example 2 says, for what values of x does the series n equals 1 to infinity of n factorial times x to the n converge? Let's take a look at using the ratio test. After all, we have a factorial, and we said in the last section that factorials are good. A ratio test is good with factorials. So let's give it a try. We're going to use the ratio test. Which means we're going to take the limit as n approaches infinity of, well, the absolute value of n, a sub n plus 1, so n plus 1 factorial times x to the n plus 1, over n plus 1, so over a sub n, which is n plus 1 times x to the n. Okay. Now, what we can do is, like we learned about when we talked about the ratio test, and we saw the factorials, we can pop off the first factor of the n plus 1 factorial. Then we'll be left with an n factorial, which will cancel with the n factorial on the bottom. And with the x to the power of n plus 1 over x to the n of those x's will cancel. Let's first rewrite the factorial. This is n plus 1 times n factorial times x plus 1 over n factorial times x to the n. You could, if you wanted to, pop off an x. That would also work. So you can see that there's an x to the n left to cancel with the x to the n on the bottom. But you can also just reason that n of these x's cancel, and you have one of these x's left. Let me close off the absolute value bars here. So what we've got is the limit of the absolute value of n plus 1 times x. Now, the n plus 1 is positive. That can come out of the absolute value bars. N plus 1 is positive. The x, however, we don't know if that's positive or negative. X is just some number, and we're actually trying to find what values of x does this series converge or diverge. Now, if we look at it, the only value of x where this limit would converge would be x equals 0. For any other x value, you're going to get n plus 1 times that number, and as n approaches infinity, that's going to blow up to infinity. So we're going to get convergence to 0. I'll write equals 0 when x is not equal to is equal to 0. Let me write it like this. And this is equal to infinity, or goes to infinity, if x is not equal to 0. Now we're interested in the case where this limit exists, so is equal to some number, and where that number is less than 1. Remember that for the ratio test, if this limit is equal to a number less than 1, so a proper fraction between 1 and 0, then the series is going to converge. So we can say, so our series only converges when x is equal to 0. That's the only time it converges. The rest of the time, for x not equal to 0, this limit is infinity, and the ratio test would say the series diverges for those x values. Again, remember that the power series is something new. This one is a different series for every value of x that we plug in. So when we plug in x equals 0, all the terms become 0 and the series converges. When we plug in a different x value, it turns out that the series diverges. So the only place where this series converges is when x is equal to 0. Let's check out example 3. Example 3 says, for what values of x does the series x minus 3 to the n over n converge? Now once again, we can use the ratio test. So we're going to take the limit as n approaches infinity of the absolute value of a sub n plus 1, where the minus come from, divided by a sub n, but rather than writing divided by a sub n, we're going to multiply by the reciprocal. We talked about doing that to save us a step when we use the ratio test. Okay, now here, the x minus 3's are going to cancel. Some of them are going to cancel. Well, most of them, in fact. And you'll be left with just one of them on the top. So we're going to have the absolute value of, and then what I'm going to do is write the n over n plus 1 on the side, and then write the x minus 3 next to it. You can notice that here the n over n plus 1 is positive, and so it can come out of the absolute value bars. We can apply the absolute value bars across this multiplication to each of these factors, and the first factor, the absolute value bars don't do anything. The second factor, it might do something, we just don't know what x is at this point. Now when we take the limit as n approaches infinity, notice what happens to the n over n plus 1. What does that approach? If you said 1, then that's correct. Now there you could, to convince yourself, you could divide the top and the bottom by n, and you'll get 1 over 1 plus 1 over n, which approaches 1 as n approaches infinity. So as n approaches infinity, that's what the n over n plus 1 is approaching. Now the x minus 3 is not doing anything. It's just staying at x minus 3 in absolute value bars. The limit only is letting n approach infinity, and that's not affecting what x is here. So this limit, whoops, change back to blue. This limit's going to equal the absolute value of x minus 3. So the limit, in the end, will depend on what x is. The value of the limit will depend on what x is, but in taking the limit, we don't really need to care what x is. Okay, so we can say, this is like our L, by the way. This is like our L. Keep switching colors. That's like our L. That's like the common ratio for our ratio test. So we can say by the ratio test, if that L value that we get, which is the absolute value of x minus 3, is less than 1, then our series converges absolutely, and so it converges. Just as an aside, note that in the case where the L value is greater than 1, the series diverges. Okay. So those are the values of x for which the series converges. But there's one case where the ratio test is inconclusive, and that's when the L value is equal to 1. So if the absolute value of x minus 3 is equal to 1, well then the ratio test is inconclusive and we have to use some other test. So there are two x values that make that happen. One of them is 2, the other one is 4. If that didn't immediately pop out to you, don't worry. We're going to do some algebra to figure out what those x values are. So, but actually, right before we do that, let's unpack what this absolute value of x minus 3 is less than 1 looks like. So absolute value of x minus 3 less than 1 looks like x minus 3 between 1 and negative 1, which looks like x between 2 and 4. Those are the two numbers I mentioned. And it's not too surprising that it's those two numbers because those are right on the boundary of the absolute value of x minus 3 being less than 1. If it's equal to 1, then we're right on the boundary at x equals 2 and x equals 4. And you can double check. If you plug in x equals 2, you'll get 2 minus 3, which is negative 1. Absolute value of negative 1 is positive 1. Same thing if you plug in 4, you get positive 1. So those x values of 2 and 4 are what give you an L value of 1, which means at those x values we need to do something else besides the ratio test. So we also need to check let me write it out here. We need to check those two boundary cases. Does the series converge when we plug in x equals 2? Does that power series converge? Let's plug it in and find out. Here, when we plug in x value of 2, we get negative 1 to the n over n. Oops. Now that series, hopefully you recognize it. This is the alternating harmonic series. This series converges by the absolute convergence test. The alternating series test. Now when you're in the middle of a bigger problem like this and you have to use one of the tests, don't worry about filling in all the details. If it were a separate problem where you just had the series and you're wondering does it converge or not, and you use the alternating series test, remember you have to show that it meets the three conditions. It satisfies the b sub n's are positive, they're non-increasing, and they're also going to 0 as n approaches infinity. But here, we're kind of in the midst of this larger problem, so we can just get away with saying this series converges by the alternating series test. Then for x equals 4, we'll have 4 minus 3 to the n over n. We're plugging in 4 into that original power series, replacing the x with a 4. And here we get 1 to the n, which is 1 over n. Now this series you should definitely recognize as being a divergent series. This diverges because it's a p series with p equals 1, or you can even say, to be extra cool, it's a harmonic series. Again, you can just write p series with p equals 1. So great, we know that at one of those endpoints of the original interval of convergence, that interval from 2 to 4, one of these endpoints gave us a convergent series, and the other one didn't. So putting this together, we can say that, oops, the series as n goes from 1 to infinity of x minus 3 to the n over n converges for the x values between 2 and 4, including 2, because we've got convergence there, but not including 4, because we got divergence there. Sometimes it helps to visualize this as well. So if you visualize what this interval looks like, you can write 2 here, you can write 4 here, 3 is right in the middle, and notice that 3 was the center of our power series, right? We said that if a power series is written in the form x minus a to the n, the center is that a. So in this case, a is like 3. So we have a center of 3. I'm going to draw that center right there. And you can see that 3, the center of the power series, is right in the center of our interval of convergence. This gives you the values of x for which the power series converges. And if we wanted to show where that is, we can put filled in dot at 2, open circle at 4, and then shade in all the x values in between. This is x, remember. So the center of your power series will be right in the middle of your interval of convergent of x values for which the series converges. Okay, let's check out example 4. Here we have another power series. We're asked what values of x does this power series converge. This one looks just off the charts crazy. It's got factorials, exponents, all kinds of stuff. So we have the series n goes from 0 to infinity of -1 to the n times x to the 2n all over 2 to the 2n times n factorial squared. Holy smokes. All right, we're going to start with the ratio test. Especially we see that factorial there. We'll think about using the ratio test. So here's the absolute value. The limit as n approaches infinity of the absolute value of the n plus 1. Whoops, where did e come from? Two to the 2 times n plus 1 times n plus 1 factorial squared. Then we have divided by a sub n, that's multiplied by the reciprocal. Whew, I hope my computer can handle this one. This is quite a monster here. All right. Now, the first thing we can do is to notice that the -1 to the n plus 1 and the -1 to the n on the bottom, you know, -1s can cancel, like n of them can cancel, and you'll have a -1 left over. But the absolute value of that -1 is going to be +1, which will disappear from our picture here. So the absolute value bars essentially annihilate the -1 to the n plus 1 and the -1 to the n at the same time. Now for the rest of it, what I'm going to do is write the x to the 2n, 2 times n plus 1. I'm going to distribute the 2 so that we have x to the 2n plus 2. Then on the bottom, I'm going to distribute the 2, and we'll have 2 to the 2n plus 2. And then I'm going to write, this might take a little bit of work off to the side, so let me make a little bit of work here off to the side. We're going to write like this. N plus 1 factorial, we can pop off one of the first factor, and we'll have n factorial left. And then the square can apply to the n plus 1 and the n factorial. So that way we're going to rewrite that particular factor so that it can cancel off the n factorial square that's on the top. We're going to rewrite it just like we did. So n plus 1 squared times n squared, n factorial squared. Okay. Now the a sub n, we're going to leave the same. Whew, my computer's really not liking this one. It's heating up. Come on, old Betsy. All right. Now we get to have a big canceling party. So 2n of these x's will cancel with 2n of these x's, and we'll have 2 of them left. See how that works? You could also rewrite it as x to the 2n times x squared, and then the x to the 2n's will cancel, and you'll just have x squared left. Same thing happens with the 2 to the 2n, and the 2 to the 2n plus 2. You'll just have a 2 squared on the bottom. The n factorial squareds cancel. And I'm amazed that anything has come out of this alive. Here we've got absolute value of x squared is the only thing left on the top. We've got a 4, and then an n plus 1 squared on the bottom. And that's it. Okay, notice that the entire expression here is positive because no matter what x is, it's squared, which makes it positive. So we can drop all the absolute value bars and you'll get limit as n approaches infinity of x squared over 4 times n plus 1 squared. Let me make that clear, that's a square. And this limit, no matter what value of x you put in here, is going to go to 0. Because as soon as x is fixed with some value, the bottom of the fraction is going to blow up to infinity as n approaches infinity, and overall the fraction will be dragged down to 0. So this limit is equal to 0 no matter what x is. So what we could say is by the ratio test, remember what we just got at the end here? This is like our L value, and here L is less than 1. So we can say by the ratio test, the series converges for all x. In other words, you could write negative infinity to infinity. That's another way you can write that. Okay, I better pause this video or go on to the next one before my computer gets really mad at me and it starts overheating. Thanks so much for watching this video, and see you in the next one.